So today I want to walk you through the presentation with the title Transformation through Integrated Modeling and Simulation. And before getting going, I want to start with a question. What is simulation, or what kind of simulation are we addressing here? Basically, it is about the approximation of reality with mathematical equations. So let's take an example. We have a geometry. Yeah, it's guiding some fluid. And in the end, what we want to do is we want to explore how it may behave in the real world. So what we're doing is we're building a set of mathematical equations that's representing the fluid behavior. We're defining boundaries, like certain inlet streams, temperatures, whatever. And in the end, if we then solve these equations, we can predict what the behavior will be. Easy as that. All that talking about mathematical equations sounds pretty fancy, but luckily we have very modern tools, so it's pretty easy to define such setups. And that's exactly giving the first statement or answer to why should I even use it? Why should I do simulation? First of all, it's way faster than physical testing. Just imagine you have to create the prototype. The simulation setup plus solving takes you a couple of minutes. Yeah. A second thing is it's much cheaper. If you have to manufacture the prototype, you have to get the capacity in manufacturing, it has to be assembled, you gotta have the testing facility, testing devices, etc. And last but not least, which is for me as an engineer the most important point, I'm getting so many additional insights. We're having here a 3D field resolution. We can slice through what's happening in the flow. Try to measure with that resolution. You cannot. You would influence the flow. Because as soon as you put a measurement device in there, you're impacting everything that's happening, right? So for me, these are the three major reasons or benefits why simulation and why I was fascinated from simulation since my studies. So let's take a look at traditional simulation loops. Typically, what's happening is we have a design process. So someone is doing CAD design in SolidWorks, CAD or whatever. And usually these design loops or iterations are rather fast in design department. You can do drastic geometric changes within minutes, hours. And at some point, you reach a situation that you're saying, okay, I'm going to freeze the design as it is. And now I want to validate what's going on. And one major reason that we have this, let's say, freeze, disconnect, I want to validate what's happening, it's the simple reason that now we need usually collaboration, because in many cases the designer or design department and the simulation specialist are two different, let's say, worlds. And another thing is that model build process, for that simple tube, it's easy. It's a couple of minutes. But depending on what we have to do to build a proper model, it can take days, it can take weeks. And that's especially true if you're looking at classical processes. I have my design freeze, I export a step file or something. Sometimes it's not even sorted, so it's just the whole assembly. Simulation specialist has to figure out what do I even want to achieve, which parts do I even need. Some geometry may be corrupted, you have to clean it up, you have to measure it. A lot of people nodding here, I guess you're working in simulation. So it's taking just a lot of time. And that's in the end a disconnect. We're running pretty fast iterations up here. Then we have the collaboration aspect, which is already a delay, and sometimes a problem in understanding, because here's a different view than here. Then we have another thing. When the model is built, we are not done. We have to solve it. So depending on how complex the model is, the simulation time can also be a bottleneck. And last but not least, just having a solved equation doesn't help me. I have to analyze it. I have to figure out what's my takeaway from that. What's the benefit? What are the KPIs I've been checking? Yeah. And the big challenge now is, in many cases, a product is not having one requirement we want to check. Let's take an electric drive, for example. We have cooling stuff, we have electromagnetic performance, DNVH performance, lubrication. All of those are different simulation models. because depending on what I want to investigate, I'm taking a different subset of the system that I want to analyze. So we're having this issue of that disconnected process, not only for structures, but potentially also for fluids, for electromagnetics. And we've been discussing this topic of different cycle times. It may be that structures model is super fast, but the fluids model is taking forever. Or I want to have the electromagnetic performance at a different stage of my design process, yeah? And what I've been experiencing a lot, my background is here in the structures, you get the task, you get the data, you spend 3 days cleaning it up, you get the result, you come back smiling to the design department and they tell you, yeah, we got new requirements from the OEM 2 days ago, thank you. Yeah, a lot of people smiling, yeah, sounds familiar. And that's actually an issue. And it's bringing several major challenges. So the first thing is, as specified, yeah, simulation cycle times usually much longer than design cycle times. So it's a disconnect. And that has a pretty drastic implication because it's really leading to that state like the designer doesn't want to talk to a simulation specialist until he's as sure as possible that what he designed is great. Yeah? So instead of getting early insights, if I have to make a decision, do I need 4 ribs on my plastics part or 3? Instead of getting that quickly validated, what would theoretically be possible, because it's an easy task, typically we end up with a cumbersome process. First design everything, simulation specialist has to remove all the details, and in the end simulation is getting somewhere at the back of the process for validation. Thumbs up or thumbs down. It causes also a bit of tension. Because as a simulation expert, if you come back to the design department and say, yeah, that doesn't work, they are not happy. And the other thing is, it can also lead to a bit of tension the other way around, because I may have some improvement proposals, how to get around it, how to solve that issue. But we are so far down the process that these changes just become overly complex. What may have been a simple task at an early stage of design is now really, really tricky because it's impacting different sub-assemblies, et cetera, et cetera. And last but not least, missing traceability between CAD and simulation. So we may have mechanical CAD data, electronics CAD data. Both may go into an electromagnetic simulation. Both may go into a thermal simulation. And in the end, the EMAC guy screams, we have to change this. The thermal guy says, we have to change that. And at some point, you figure out, OK, they've been working on freeze whatever, and they've been working on freeze whatever. And everything is out of sync, causing a lot of tension again. So what is our answer to that? I think you've heard about the term already in the mains plenary. Our goal is to combine modeling and simulation to ModSim. And with ModSim, what we're meaning is, in the end, it's unified modeling and simulation on a common data model. It's not one CAD here, one simulation there, export, import, whatever. It is one data model. And what is also very important, on a single user experience. So it's not like if I'm in the CAD world and I want to do a simulation, I'm switching completely tools or something, or the other way around. Because it makes adoption very, very hard if every tool is looking different. In my simulation experience, I've been working with different pre-post systems, etc. Just switching from one pre-post to the other is like a mess. It's not turning on the right buttons, whatever. It's not fun. So to give a little bit of an illustration, what we do mean by integrated modeling and simulation on a common data model, let's take a look at a short video. So what we're seeing here is an electric drive unit. And the nice thing is we're bringing the best of CATIA, which is fully parametric modeling with everything around it, all the information we're having in a CAD model. So we're working with configurations here. The full assembly can update fully parametric. And from a simulation perspective, the very, very nice thing is now, we are now not exporting the step file and do all the work all over again, but we have defined defeaturing rules, meshing rules, so the whole system is updating automatically. And as we're working on a common data model on a database, we cannot have just one mesh associated to that, not just one model. We can have a fluids model connected on this subset. We can have a structures model for the whole NVH. We can have a structures model for detailed analysis. They can all be assigned to that. And now I want to step into two typical applications. Because what you've seen before is a technology, right? That's a basis. But what can we now really do with that? And one thing that customers really appreciate is you can define very easy to use guidelines for designers. So if you're a simulation expert, maybe you know that situation. You have tons of highly complex stuff to do. And then someone comes around with, yeah, I have here 4 solid parts and I want to know the eigenfrequency. And you're like, come on. That's not something I should be doing. And it will distract you. It will distract you from what your expertise is really needed for. And think about the cycle time again. An eigenfrequency analysis is something that takes a couple of minutes. So if the designer could trigger it himself, he could get answers very easy, very early. And that's exactly what we're doing here. So we're shifting easy-to-use guidelines to designers. We're shifting simulation to the early stages of the process. And therefore, we're making simulation available to drive innovation. It's not a validation tool anymore. We don't care about the last digits behind the comma. It's really about getting an idea and understanding of how my product, my sub-assembly, my part is behaving. And from that very theoretical, abstract description, let's take a real-life example. It's automotive-driven. We have a car door. And we can see here, we can define typical use cases, right? And now what a designer can do, if he's leveraging the system, he's just picking the method he wants to do, like door seg analysis. What we're seeing now is we're having a very nice assistant panel, and this is customized. It means the options we're having down there are very limited. It's describing, take the inner panel, which mesh size. Take the outer panel, which mesh size. So in the end, we're putting a really clear guideline what to do. It's not about releasing or signing something off. It's about getting a basic understanding, okay, if I have this design, what happens? If I put some beads into the sheet metal, what happens? Yeah? And that's really something we can pretty easily shift. We can embed some pictures, pictograms, etc. And what's really important, you can put, from a numerical point of view, highly complex things in the hands of designers if it's well-defined, because you're removing all the other options. So if the designer should only put a clamp, he can only pick the clamp, right? So not many issues of simply defining a wrong model in itself because there are 20,000 options to create a boundary. Same accounts for the loads. Not many options. Force, picture, please put it down there, and it's down there, and I can solve it. Now, another example, which is going more to the high-end range, let's say, because this was really simple, right? It's nothing tricky. But we can automate highly repetitive tasks. We can explore many, many options. When you've seen the drivetrain, it's a fully parametric model. So why should we manually edit a parameter, then send it to someone else to simulate, and then analyze the result? Why not just explore the design space with all the options that make sense, and afterwards pick the 2-3 options that are the best, and decide on those 2, 3, 4 options which are the ones I want to proceed with, right? And this can look, for example, like that. We're having here a complete body in white, and for the roof section, what we want to do is, we're seeing that stringer here. We're reading in the parameters, we're unlocking them, and now what we're doing is in the end a model check. So all the different design parameters, we're not solving the simulation because that's time consuming, yeah, that's cost. But we're just checking, is my geometric model updating, is the mesh working, is my scenario definition working? Just a pre-check. And once we figure out, yes, it's all robust, it's working, we can now go ahead and define, like, what's my maximum displacement of the roof, what's the eigenfrequency I want to see. I want to minimize my mass. And in the end, I can just hit it and submit it. Not sure if you've seen it, simultaneous 10 jobs. Now, many customers, when they see that, they're like, I don't have that computing capacity. But there comes a very nice other aspect into play. Our solutions are on cloud. It's software as a service. So you don't have to have a big own HPC. You don't have to have simulation licenses for hundreds of thousands of euros a year. Because such scenarios are an on-demand thing. It's something I'm doing, I don't know, a couple of times a month, potentially. But when I'm doing that, I really need HPC. And that doesn't mean 10 cores or 20 cores, it means really scale it up. Many jobs in parallel. I want to have, I don't know, in 5-6 hours the results to take a decision, right? So, in the end, we want to get away from that traditional process, and we want to get to that ModSim process. We don't want to have our highly experienced engineers drawing elements. Sometimes it's necessary, yes, but in many cases it is not. And wherever it is not, we should be very cautious with the time, with the know-how of our engineers. So this concept of modeling and simulation, this ModSim concept, is forming the core of what we're talking about. But there's more to it. Because we're never doing simulation for the purpose of simulation. We're doing simulation because we want to understand what's happening. We have KPIs we want to check. We have requirements we have to validate. And if I have to do that, and I'm having electromagnetics requirements and structures and fluids and whatever, I have to upfront be aware of, okay, what are my requirements? With what test cases can I check them? Okay, eigenfrequency, that's a structural test case. And it's this kind of simulation. Drop test is a different structural test case. Thermal behavior is another test case. So what we're doing here is we are putting in context the requirements we have with the test cases we have. And behind the test cases can be simulations, but can also be physical testing. Because we need to have a holistic view of our validation strategy, right? And that's also a very big benefit in the end, because besides the fact that we get really efficient in tracking, are we sending it to simulation or a physical test or whatever, it's giving me also the chance to sync my simulation results with the test results. I'm not sure what your experience is. So here we're seeing, for example, for the electromagnetic test case, efficiency, maximum torque, etc. So different requirements below. We are having here the link also. For example, we can put the results in here. We have the association to the assembly. We can review it. And it's having two advantages. The first thing, the results are available to anyone having access to the platform who has the need or the right to view them. So it's not like the simulation results are with the simulation expert and in a PDF report that nobody reads anymore. So it's very easy to track and watch. And another thing, where I just interrupted due to the video, I don't know your experience. My experience as a simulation expert in my past days, I never get feedback from testing unless something goes wrong. So I can never improve or validate my models. That's helping a lot. Because you would have, for a certain requirement, simulation test case, physical test case, and in the end you can log into it and see, oh, I was 20% off. Great, it's in the right direction, but I have an issue with my model, right? That slide is very nice, and it's touching the point of traceability. I already mentioned a bit like different simulation disciplines, different mechanical CAD, ECAD. In the CAD world, PDM, PLM, it's a standard. As soon as you're having more than 5 designers without PDM, nobody will work. The issue is in the simulation world. We have a test case here. We have a simulation. We have an assembly. The assembly is out of sub-assemblies. And each of those assemblies, part sub-assemblies, may have a different revision state. And now imagine you're not working on a common data model, but you get a step file. Good luck. And especially if after 2 years you have a warranty thing or something and you figure out, my material code for this plastics material was wrong. Try to find what was affected. Common data model helps a lot. And it's not a huge value for the simulation engineer in himself, but for the whole company. That's really important to understand. Now, one example for measurable benefits. Maybe everyone knows the plastics bottles for shampoo and stuff. Was a very nice reference at one of our ModSim conferences, recorded. Just Google for the systems and ModSim and you will find the community and everything in there. We have statements from PepsiCo, Unilever, from Nio, from Renault, from whoever. And they had a situation that the specialists optimizing those bottles said no chance to make them any lighter while fulfilling the requirements. They managed to cut 20% of the mass, saving 100,000 tons of resin a year, sustainability, saving 120,000, here we have the 1,000 in dollars, and reducing the fuel consumption. I mean, they have to be delivered somehow, right? So trucks have to run them. And it's exactly taking that concept. You have the requirements, you have a process that's automatically optimizing parameter studies for different requirements at the same time. So especially if you have a multi-objective optimization, where the objectives may point in different directions, this is really becoming super powerful. And key takeaway, what took us 10 months to get here is now taking 3 weeks. Now, the title is transformation. So why is ModSim a transformation project? Well, first of all, you have multiple departments involved. If you're putting some workload to a designer, he's first of all going to be complaining because he has something additional to do, right? So you have to make sure that they understand their value, what's in it for them. If you put simulation to a designer, you may have pushback from the simulation experts. They will be blocking my licenses. So it's a shift in scope of work and responsibilities. If you're really talking about that full ModSim, leveraging CATIA knowledgeware with templates and everything, to get a really highly stable and robust process, it may mean that a CATIA V5 user at some point has to go to 3D Experience CATIA. It may mean that a simulation expert needs to change his beloved user interface, right? So we have a change in tool chain and behavior. And these points is something you cannot start just in a simulation department. It's not something you can start just in the CAD department. It's not an IT decision. It needs a high-level understanding of where do we want to go, why do we want to go there, and a clear plan, whom to get on board, when, to find the champions in your company that are open for that see the benefit. Okay, I don't have to wait 5 days for the simulation. I can do it myself. The simulation expert who sees, okay, I can focus on my core knowledge, building the process. I don't have to operate it myself over and over again, right? So in the end, what we're aiming for with this transformation for integrated modeling and simulation is we want to get simulation from the validation, thumbs up or thumbs down. We want to get it in as early as possible to support the concept phase, to support the detailed phase, and also shorten our physical testing. We want to get as much confidence as we can before we go to the physical test booth. So we're at the Innovation Forum. In the end, we want to go from validation to innovation. We want to drive our developments. With that, I'm happy for questions.